Okay, so after day one of exploring how to do translations of functions, you should understand that you can take any function in any family and you can slide it up, down, left, right by adding something into the equation. So one of the things I want to do is demonstrate here how this can work with different families. I also want to make sure that we understand that the original guy stays congruent to himself. He's just being slid around, but his shape is remaining intact. So let's look at a quadratic example, right? Quadratics are used because it's pretty easy just to trace where the vertex is moving to see that, well, what happens if I take it and I add k. And you notice here k is on the outside, so it's going to affect the output, and then that means it's going to affect the y value. So right now k is 0. If I make k be 5, it moved up 5. If I make k be negative 4, it's going to move down 4. Okay. Notice that every point moved down 4. Not just this point moved down 4. Let's look at the point that was up here at 4. Boom, it moved down to 0. Or this point that was at 4 moved down to 0. Look at the point that was here at 1. It's going to be at negative 3. Okay, so every point on the red graph moves down 4. Right? Same thing if I moved it up, they'd all move up the same amount. So let's say I want to move it up 2. Every point moved up 2. This point's pretty easy to see it moved up 2, but look, this point was at 1, and now it's at 3. This point that was at 1 is at 3. The point that was at 4 is now at 6, right? On the red graph, this was at 4. On the blue graph, it's at 6. Same x value, but the y value went up the same amount. All right, there's a quadratic. We'll move a little more quickly with the other ones. Absolute value is another one that they use a lot because, well, let me turn this guy off. Right. Absolute value they use because, like a quadratic, it's a U shape, it's very easy to see how the points are moving. So right now, here is just absolute value of x. What if I want to add something to them? Again, it's on the outside. It's going to affect the output. That's going to make it move up and down. All right, so when k is positive, it moves up. K is negative, it moves down. So one of the clues that we need to pick up on is that where the k is, it's outside, it makes it move up and down. Versus when it's inside, it affects the input. Okay, this is what you put into the function. That's in the parentheses. So that's the input is your x variable. So you can see that when you make it inside, it moves it horizontally left to right. Okay, now notice when I make it negative, the graph is moving in the positive direction, and when I make it positive, it's moving in the negative direction. So right now, it's at positive 4, and it made it move to the left 4. Every point moved to the left 4. This vertex point's very easy to see, but this point moved to the left 4. This point moved to the left 4. Every point moved to the left 4 versus every point moving to the right. Let's see if I can get it on 4. Boom, there we go. All right, so this point moved to the right 4. This point right here. No, this point right here moved to the right 4. This point was here. It moved to the right 4. So that's how it works with the absolute value family. Okay, so let's look at some other families. What if I have a cubic example? All right, I wanted to do more than one cubic example. Here's just plain old x cubed. Okay, we can move them up and down. Notice it's on the outside. We're going to move them up and down. When x is positive, it moves up. When x is negative, it moves down. Okay, that's on the outside. All of a sudden we put the k on the inside. It's going to move them left to right. Okay, k is positive, it moves left. K is negative, it moves right. Usually the easy point to look at is right here, this inflection point. But 1, 1's a pretty easy point to look at too. So for example, let's make this a nice number. So 1, when x is 1, y is 1. Now when x is 6, y is 1. So I could see it moved forward 5. Went from being at 1 to 6. All right, so that's a nice point to sort of look at as well. All right, but there are other cubic functions. Matter of fact, you're more likely to see a cubic function that looks like this. Okay, so those any function can move left or right. It doesn't have to be a parent function, right? X cube's the parent function. This is just another family member. So if I want to move him, I can move him up and down. Again, notice he's staying completely congruent to his original self. He's just moving up and down, right? Versus now we're going to move him left to right, but he stays congruent to his original self. But here it's sort of more challenging to figure out what points am I going to follow. Sometimes it's nice to pick the y-intercept. If you have nice friendly x-intercepts, use those. But in this case, we don't. This one's a nice friendly point, though. Here's a decent point, and here's a decent point. So you can say, like, well, where did they move to? So let's make this a nicer number. All right, so this 2, it's at 0, so this is 0, 2, and it's going to end up being at 6, 2. So it moved forward 6. At this point was at 2, 2. Now it's at 8, 2. At this point that was at negative 2 is now at 4, because negative 2 plus 6 is 4. Okay. Lastly, let's see. Let's just real quick show you square root family. Looks like this. You can get moved up and down, right? You can get moved left and right. Any family member. Okay. And we really didn't do too much with the exponential, so let's look at an exponential example. I just made this random one up, right? We want to move them up and down. Let's move them up and down. Okay, he's moved up 2. Again, I would probably use the y-intercept to sort of see that. Move down 2. Okay, he can get moved left and right as well. So now, moving forward, moving backwards. So he's less obvious that he stays congruent to his original self, but he really does. He's just moved forward or backward. So that's why they tend to use the quadratics and the absolute value families for those types of examples. But I'm hoping that sort of solidifies the idea of when k is on the inside, it'll affect it horizontally. When k is on the outside, it affects it vertically. Okay, if it says plus, it goes up, minus goes down. Here, if it says plus, it goes to the left, and minus, it goes to the right. So those are some of the things that you probably want to put on your graphic organizer if you haven't already.